Hey all dear students, once again in the Irodov solution series, I have this question number 3.29 of Irodov. The question states, inside an infinitely long circular cylinder charged uniformly with a volume density rho, there is a circular cylindrical cavity. The distance between the axis of the cylinder and the cavity is equal to A. Find the electric field strength E inside the cavity. The relative permittivity is assumed to be equal to unity. So this again is similar to the previous one of Irodov 3.28, in which there was a spherical cavity inside a sphere. Now we have a cylindrical cavity inside a long circular cylinder, uniformly charged density there is 0. So before I find electric field at a general point inside cavity, I will derive an expression for the electric field at an interior point of a uniformly charged solid cylinder. So let's go ahead. Here is a very long solid cylinder having a uniform charge density rho, and this is the axis, its radius is r. I want to find electric field at a general point, say point P, and before going ahead, I will define my radial direction. Because it is a cylinder, now the radial direction is perpendicular to axis at any point like this. If this is the axis, so this is my radial direction, this is my radial direction, this is my radial direction. Unlike in the spherical coordinate system, the direction are with respect to the origin. So there the radial direction at this point is like this point is like that. So a unit vector in the radial direction is this r cap, which is perpendicular to axis. And I want to find electric field at P, which is at a distance r from the axis, and the vector distance is vector r. So vector r can be written as r into r cap. So now to find electric field at P, I will have to take a Gaussian surface which passes through P. So symmetry of the situation tells me that I should take a Gaussian surface, which is a cylinder whose axis coincide with the axis of the original cylinder or something like that. So this is the Gaussian surface that I have taken. And suppose this Gaussian surface, which is a cylinder, has a length L, radius R. So one thing that I will do, first of all, I will find the Q enclosed within that cylinder. And that will be obviously this whole setup has a uniform charge density rho. So Q enclosed is a rho into volume, which is a pi r square into L. And now in this Gaussian surface, say S, I will apply Gauss law, which is integration of E dot ds is equal to Q enclosed, which is rho pi r square into L divided by epsilon naught. This integration has to be computed in three surfaces. This is surface 1, this is surface 2, and this is the curved surface 3. You can see clearly electric field has to be by symmetry, has to be radial direction. In surface 1, the area vector is along the axis, obviously normal to the surface like this. And here also area vector has to be like that. And electric field at any point would be like this, like this. Here also electric field would be like this, like this. So on surface 1 and 2, at any point, E would be perpendicular to the area vector here also. So the flux at surface 1 and surface 2 would be 0. At surface 3, at any point, electric field has to be radially outward direction. In the same direction, area vector would be there. So symmetry of the problem tells me that at any point of the surface 3, E is parallel to dA, and at any point, the E will be same in magnitude. So here that E dot ds will become on surface 3 will be E into total area of surface 3, that is a 2 pi r into L. So this is rho pi r square L by epsilon naught, and this L gets cancelled, 1 pi will get cancelled. So in magnitude, I will get E is equal to rho by 2 epsilon naught, and R would be here. And now because this electric field is along vector R, So this E vector I can write in terms of vector form, rho vector R by 2 epsilon naught. Now we are ready to apply this result for to find electric field inside a point in cylindrical cavity, like in the previous case. So here, this is a cylinder, solid cylinder having charge density rho, and within that there is a coaxial cylindrical cavity. So to find electric field at an interior point A, so I want to look from top. So I want to look from the top. So this section, this cross section will look like this. So here is that general point, and that is where we want to find electric field. And once again, what we will do, I'll put volume charge density rho. Here I will put two volume charge densities. One rho and one minus rho. So on putting a volume charge density rho, I will have a one complete cylinder of charge density rho, whose center or the axis atom. And on putting a volume charge density minus rho, I will have another cylinder whose axis is passing through that O dash, and using the previous formula, we will find the electric field at A. So electric field at A, let me call that this one is a 1 and this one is 2, is electric field at A because of 1 plus electric field at A because of 2. So electric field at A because of 1 would be rho by 2 epsilon naught vector R. Vector R had a tail at the point on the axis and the head at that point. So that vector R is my OA vector, like this. And then similarly, because of the reason 2, that the cylinder 2, the same formula, but here the rho is minus rho divided by 2 epsilon naught, and the vector R. Now the vector R has a tail at O dash, and we have to find electric field at O, so head would be at A. So this vector will be O dash A vector. So rho by 2 epsilon naught OA minus O dash A. And see clearly, like in the previous question, this OA minus O dash A is nothing but the A vector. So we will have rho by 2 epsilon naught A vector, and that is our answer. So once again, we have got that this electric field is uniform at any point inside the cavity region. Suppose we are here. So we are here. So this electric field is along this direction. This electric field is along this direction. This electric field. So we are getting a uniform electric field inside